Uh, it's my great pleasure to be here. And first of all, thanks for inviting. And I'm very glad to see a lot of people today, and I hear a lot of excellent talks already. So today I'm going to talk a little bit about the sensing and the acting aspects that are both important for realizing embodied AI. So before getting there, let me briefly talk, about Microsoft Research Asia Tokyo Lab, because I'm, quite often asked the question, what it is like. So first of all, it's very small, and you will see in some photo. So we started this new laboratory of, Microsoft Research Asia in Tokyo last year, November 18th. So it's about 1 year old. And when I joined, I was kind of only one person, sitting there. And it was a very interesting experience to starting up a new, you know, laboratory. It's almost like you are starting up a new lab in a university. So anyways, so speaking of Microsoft Research, I guess, if your background is robotics, you probably don't know about Microsoft Research because Microsoft Research has been focusing on computer science rather than robotics. We haven't been doing anything in robotics field in the past. So we are nobody in a robotics field. But now we are interested in robotics, but particularly on the aspect of robot learning instead of hardware itself. So that's what we are working on. And we have a bunch of labs scattered across the world, and some of them are bigger than the others, like Redmond, Cambridge, Beijing labs are bigger. But there are also small regional labs located anywhere in the world. And in Asia Pacific, we have a few labs. The oldest one is Beijing, established in 1998. And the second one is Shanghai. Then we opened Vancouver. And the last year, we opened the Tokyo lab. And this year, in summer, we started a Singapore lab. So Tokyo lab is based in Tokyo. And this is one of the photo from our office. And inside is kind of, nicely decorated. And the view is great. Desks are okay. And so that's, this is where we are. And currently we only have a few people. This is all of us in Tokyo. And that's myself. And so Mao is, she's not a researcher, but she's, helping a lot for us. And we have 3 full-time researchers. One is a computer vision researcher, and the 2 of them are robotics researchers, and we have 2 interns right now. So we are, because we are so small, we need to focus on some topic. And what we are working on is embodied AI. So we are, looking into this space. So embodied AI, as you may know, it's an AI agent that interact with and learn from physical environment. So there are a few reasons that we are looking into this domain. One is that, because we are in Tokyo and there are a lot of, leading robotics companies in Tokyo area, such as Kawasaki, Honda, and Honda is well known for Asimo robot, and they are still continuing robotics research. And we are partnering with those leading companies, hardware companies, to realize, our vision. And also, I guess it's probably a shared problem, between Korea and Japan. And we are anticipating labor shortage. In 2040, we are expecting, the shortage about 12 million people shortage. So that's a significant, number of people. So we need to be more efficient. And one of the solution may be embodied AI to make us more effective in doing anything. So that's why we are looking at this domain. And our vision is to connect AI with robotics. So at Microsoft Research, we see ourselves as, software people. And we know how to do AI thing, but we don't necessarily know how to do hardware. But, we partner with hardware companies. Then, we try to put them together to realize, embodied AI. So at a glance, embodied AI at high level planning, it seems to be working pretty well because large language models nowadays are very good. So if you provide some, question to large language model, it can tell you, what to do. For example, let's say I give a prompt like I'm a mobile robot with one arm with two finger grippers. Then how do I cut sashimi? Say it can actually, this is a high level task, but it can decompose it into subtasks that are more, manageable by simple robot. Then it starts to break down the process of, by decomposing this high-level task into smaller subtasks, like, gather necessary items, locate ingredients, and prepare fish, hold the knife, and so on. This is great, but what's missing is that, although it's descriptive, but it's not grounded really to the physical world, environment and action. So it seems to know what to do, but it actually doesn't really tell you where to find the knife. What does it mean by hold? Those kind of things. That information is missing here. So to achieve, the real embodied AI, from our view, two components are still, very limited. One is sensing, and the other is acting. So sensing part, we tend to consider that once we know the 3D shape, color of the object in the real world, we tend to consider that we understand the real world. But the real world is much more than shape and appearance. It's about the stiffness or friction, weight, how heavy it is. So those kind of information is still very difficult to extract from the reality. So I'm not going to talk about that because we don't have a way to do that right now. But in the future, we definitely want such a capability to sense the physical property of the real world. So let me briefly talk a little bit about real world sensing from images. So mostly I'm going to talk about something that we can reasonably achieve today. But I'm going to argue that traditional model-based approach and the advanced learning-based approaches can work together to achieve this goal in the end. So anyways, let me start. So let's think of a task of recovering some scene parameters or scene properties from images, image observations. So given image, we wish to estimate the shape of that object, or we might want to estimate the material of that object, or we may care about the illumination environment of the scene. And let's say image is Y, and the parameters that you wish to estimate is theta. So this problem is essentially computer vision problem. By the way, my background is computer vision, so I don't know much about robotics, but I know a little bit about computer vision. Okay, so, okay, good. This problem is generally ill-posed problem. You cannot really estimate anything just from image. Why? Because vision is inherently ambiguous. So given an image, let's think of inferring the shape of the object. So what do you think of the shape of this object? I believe most of you think this is bunny, and you kind of imagine the standard shape of this bunny. But it's unclear whether that is correct, because the same appearance can be produced by different combinations of illumination, color, and shape. So if you properly combine those shape, light, color, information, then you can produce exactly the same appearance, just like on the right-hand side. This is the appearance of those properties combined, meaning that the leftmost is right direction where you are illuminating the object, color of the target object, and shape in the form of a surface normal. Then if you render the scene using those properties, then you get exactly the same appearance. So which indicates that there exists one-to-many mapping in an image to scene appearance. So given, let's think of a space of all possible images and the space of all possible scene parameters. A point in that space of images forms just observation, one image. Then that may correspond to a set of points that forms a manifold in the space of scene parameters. So any of those points can be a solution because they can produce the same appearance. So in graphics, that's not a problem because we tend to begin from the scene parameters. So once we define the scene parameter, then we can uniquely determine its appearance using rendering method like ray tracing, whatever method. But the other direction is a computer vision problem. It's not clear whether we can really solve the problem. We can solve the problem, but is the solution something we really want? So that's another question. So does there exist F inverse? If F is a rendering function, then does there exist F inverse? So that's kind of questionable. But this is what we want to solve, and so I can see two distinct approaches to achieve F inverse. So one is obviously learning-based approach. You can train your network to associate some image to scene parameter, so that once properly your network is trained, you can expect to recover scene parameter from image input. So for example, single image depth estimation, it's an impossible task in, mathematically and geometrically. It's an impossible task. I just want to remind you. So people tend to think that this is doable right now. This is a solved problem, but it's not. But if you learn it, then you can expect some output can be produced based on what you have learned before. But it's different than really solving this problem. Okay, but anyways, learning-based methods are great. And so I have no objection about it. And so you can expect reasonable scene parameters if your network is well trained. So this is one type of approach. The other approach may be model-based approach. So model-based approach is like a traditional approach. You work with some equations, then try to estimate the scene parameter using that equation. And the equation is given in a kind of, direction from scene parameter to images. And let's say such image formation model is f, some function, some complicated function that takes parameter theta. Then what typically done is to, minimize the loss between image and rendered image by moving the parameter theta so that you can find some optimal, parameter theta star. A simple example would be some shape from shading with Lambertian assumption, where you assume some very simple image formation model. Image Y is produced by some dot product of surface normal and illumination direction. Then you solve for, those unknown parameters, scene parameters, rho and n. So I'm not going into detail of this. But anyways, so it begins with establishing some image formation model, then solve for the parameter. In a more sophisticated one, you can rely on differentiable rendering. So I believe some of you may heard of this. So this is nothing to do with neural net, but it uses GPU probably, if you care about the speed. So it basically begins from, it's still a model-based approach. You need to know the equation that converts scene parameter to image. So that's needed. Then this differentiable renderer takes the scene parameter theta to produce an image, Y. Then, because it's differentiable, by defining the loss between the rendered image and the observed image Y bar, you can define loss. Then you can backprop the gradient computed from this loss in order to update the scene parameter theta. So you begin from some initial value, initial guess of theta, then you try to render, then compare with the observation photograph that you take, then you backprop to update the scene parameter theta. Okay, then if you iterate that process, the scene parameter gradually gets closer to what you want in a way that the loss is getting smaller. Okay, so then I talked about learning-based and model-based methods, and they are you know, both of them are good, but, they have different, behaviors. Learning-based methods clearly assumes that the test data is in distribution of training set. So you are implicitly assuming that your test data distribution is similar to the training set distribution. So if your test data is in distribution, then you can expect that your estimation is on the manifold that is considered good as a scene parameter for that image. But your test data is out of distribution, then you don't know what's going to happen. So that's a hallucination case. The same happens for model-based methods as well. So if you start from good initialization, then you may expect you reach a good point on this scene parameter manifold. But if you begin from bad initialization, then you may stack to somewhere off the manifold. So they have a similar property, and sometimes work, sometimes do not, and so that's the reality. Then, which is better then? So that's a question I'm always wondering. So there's a learning-based method, there's a model-based method. There may be pros and cons. So speaking of capability of handling diverse real-world data, it's kind of obvious that learning-based method is much better compared to model-based method. Because model-based method, you need to define some equation, and which is quite often very simple, too simple to describe the reality. So speaking of extrapolation ability, the capability of dealing with out of distribution data, maybe model-based methods is safer because you can always expect, the range of the output because you know the equation. You can always restrict your output to certain range. Learning-based methods, on the other hand, it's unclear how to avoid the hallucination thing. So computation efficiency, so this is kind of, questionable. I don't know for sure. But typically, in a supervised learning case, you spend a lot of computation before testing, right? For training purpose, you spend a lot of computation. But once trained, testing is very efficient. But model-based method, you always require certain amount of compute every time you have the test input. Then handcrafted or not. So model-based methods are quite often accused by that they are model-based methods are handcrafted. You just manufactured this equation, so it shouldn't be accurate. So that's a kind of criticism that the model-based methods often take. But if you look at the neural net architecture, they are also handcrafted. You do this Lego block combination thing. So you put the transformers and whatever. So I guess from my view, both of them are handcrafted. So anyway, my view is that they have pros and cons, and they probably meet somewhere in the middle. Eventually I think learning-based method takes over everything, but in the meantime, I guess those two approaches work together to achieve our goal, especially in a case where we don't have a large amount of data. It was emphasized in the morning talks that data scarcity in robotics is significant, then how do we solve that problem? So I used the example of image, recovering a scene parameter from images, but it also applies to our action generation context as well. But anyways, so for sensing, I believe that more sensing capability is necessary for really achieving the goal of embodied AI. So we should start thinking of, deviating from the current RGB camera or RGBD camera. If you are only using RGBD camera, I don't think we are going to achieve the goal of embodied AI. It's too limited to sense the reality. So that's why I consider computational imaging continues to be important. So we wish to have more sensing capability. Then by having that, I think learning-based method and the model-based method together grow with much more capability. So let me give you one example of computational imaging. So this is my favorite topic of photometric stereo. So it's a kind of interesting way of recording, observing the scene. So that's something called computational imaging. So suppose you have an object and a camera, and you illuminate the scene from somewhere, then take photograph. By retaining the position of object and the camera, you don't move them at all, but you only move illumination. Then take another photograph. Then you repeat doing this for multiple times. And by having such observation, you can observe, you can compute the surface normal of the target object very accurately, quite often. So surface normal is like a 3D vector in a 3D space. So a vector that is perpendicular to our surface. Okay, so it has a history, and the conventional photometric stereo was developed in 1978, and with our model-based approach, of course, you write down equation of image formation, then you try to solve for surface normal. That's the original photometric stereo. Suppose you have one pixel camera observing a plane, and let's say your brightness measurement is M1, then you know the illumination direction in 3D space. It's a vector, 3D vector, L1, and you wish to determine the surface normal N of this plane. Okay, that's the problem setting. Then you change the illumination direction, which is also known. Then you take another photograph to obtain another observation, M2. Then M3, and so on. So once you have a set of observations, you can establish a linear system of equations, just like this. M is a measurement vector, and you wish to solve for surface normal N by solving this linear system. In reality, though, it's more complicated because things are not necessarily Lambertian. So then, there may be some complex reflection, like specular reflection, which do not obey Lambertian reflectance. By the way, Lambertian reflectance, if it's your first time to hear this word, don't worry. It's really about, that your scene point appearance does not change, even if you change the viewing direction, which is quite often assumed in robotics and also computer vision. But anyways, so specular reflection is not like Lambertian reflectance. And depending on where you see the object, the appearance of object may be different. So that's a specular reflection. And another thing is interreflections. Lights are bouncing off of a surface toward other surface and bounce back. So there is a kind of infinite number of interaction of light with the scene before getting into your eye. So that's something called interreflections. So these are not very difficult to model. Therefore, people started to develop this differentiable rendering in a model-based approach. So differentiable rendering, as I explained, it's a graphics renderer, which is differentiable. So in the case of surface normal estimation, let's say this is your target surface normal. And you begin with some initialization when you want to use our differentiable renderer. You start from some initialization. Then what you do is that with that initialization, you try to render a scene to generate the image. Then once the image is generated, you compare that image with your actual observation photograph. Then compare. Then the loss is naturally defined. Then you can backprop that loss in order to update the surface normal n. Then once properly trained, the surface normal is gradually updated to become close to the reality. The same problem can be solved, of course, by learning-based methods. So in this talk, I'm talking about the model-based and learning-based method. And this differential rendering is a model-based approach, which is pretty popular in graphics, I think, still. But not much in computer vision or robotics, I guess. But anyway, so this is one approach to solve the problem using model-based approach. And of course, you can rely on learning-based approach to solve the same problem. So this is neural photometric stereo. So given a set of images under different illumination conditions, you can associate those set of images to the surface normal that you wish to obtain by training a neural net. And of course, you can prepare for the training set using some graphics rendering. And so this one, so we did a long time ago, almost 10 years ago. And we had a kind of, state-of-the-art result at the time. And afterward, it's been developed in many interesting ways. There was a neural inverse rendering idea, and also self-calibrating photometric stereo, which tries to estimate the illumination and the shape at the same time. So this, neural photometric stereo with unknown lights is, the input is the same, basically. You take a set of images recorded under different illumination conditions, and then it first tries to estimate the illumination distribution. Surprisingly, you can estimate the illumination direction by properly training the neural net. And then finally, it outputs the surface normal. So it turns out to be pretty effective in producing accurate shape information. So the top row is showing the different scenes recorded under different illumination conditions. And the bottom row is the surface orientation that is computed by our method. Okay, so afterward, of course, there are more developments with a modern architecture like transformer and so on. And I think it's still a active topic. So another interesting thing I want to talk is a single image 4-color photometric stereo. So this one is interesting topic. So suppose you have illumination source with different colors, different wavelengths. Then you can assume that you put those 4 light sources somewhere. Then if you have a 4-band camera, so RGB is a 3-band camera, but we need 4-band camera. Then you can observe the individual contribution of those lights at a single shot. Every frame you can record the contributions from those illuminations. Then we can recover the target object shape for each frame. So this is a kind of very interesting finding. And surprisingly, you cannot solve this problem with 3-band camera. You need 4-band. And even if you increase the number of bands to 5 or 6, it doesn't help. So 4 is the key. It's very interesting. If you care about this kind of discussion, it's a very interesting paper to look at. And the other thing, which is very simple, is a symmetric light arrangement in order to achieve photometric stereo. So basically, the idea is, arranging the illumination or LED symmetrically with respect to the camera. Then by doing so, you can do a very simple computation just by subtracting one image captured under 1 from the image captured under illumination 3, just subtracting, image subtraction. Then you do the same vertically. Then by combining them, you can obtain the azimuth angle of the surface. Azimuth angle is like a projection of surface normal onto your image plane. So you know which direction surface is looking at just by this subtraction and the division operation. So this is very interesting. And this azimuth information is not a full information of surface normal. So it doesn't give you the full information of shape, but it's very useful information about shape. And we actually found that this azimuth information is already useful for multi-view stereo setting. So in multi-view stereo, you need to find correspondence so that you can triangulate to determine depth. So that's structure from motion and multi-view stereo. But for specular scene, highly specular surface, it is difficult because you cannot find the correspondence. But for this kind of highly specular scene, we can use polarization camera, polarimetric camera, in order to obtain azimuth map. So you can, it's a kind of a special camera, but you can still purchase. From this kind of scene, it's kind of easy to obtain azimuth map using polarization camera. Then, so what this paper is about is that this polarization, this azimuth angle is sufficient for determining the correspondence across multi-view. Well, sufficient is probably too much to say, but basically given azimuth map, there exists some tangent space that is useful for associating the same points viewed from different viewpoints. So they live in the same tangent space because they should share the same surface normal. And this tangent space analysis is a kind of a new geometric cue for identifying correspondences across multi-view when only given azimuth map. So if you know surface normal, then the problem is much easier. Because sometimes surface normal is not accessible, but you can only access to azimuth map. Then in that case, this kind of geometric constraint is pretty useful. Okay, so I move on. Then with that, we can, this is a kind of, these are photographs taken under different illumination conditions from multi-view. Then from that image, we can reconstruct the scene shape and appearance very accurately. So this is a rendering of the reconstructed scene. And also even for shiny surface, you can observe, small details on the surface and the reflectance of the surface faithfully recovered by this computational imaging method. Okay, so, but again, these are still very limited. We don't, so what we are measuring here is only 3D shape and reflectance. But the reality has more than that. We want to know how hard or soft the target object is, stiffness and weight, the mass of the object, and also friction between two objects. So those information is something we definitely want to, access. So sensing still needs to go. And what we are working, so if you care about computer vision remains to be important. So I can, assure about that. Okay, then I move on to acting. So how to generate action. So yesterday, I was working with Sonju, Professor Kim, and he mentioned about the Moravec's paradox. So I just wanted to say the same thing to every one of you. So this is a paradox said by Moravec and rephrased by Pinker later. The hard problems are easy, and the easy problems are hard. So we tend to think that, intellectually difficult problem, like Go, playing Go, seems to be, it's difficult for human. But it turned out to be easy for computers. On the other hand, things that we consider easy, like, manipulating object, grasping object. So that kind of things that we unconsciously doing turned out to be very difficult for robots. And at Tokyo Lab, we are interested in dexterous manipulation with a multi-finger robot hand. And compared to two-finger gripper robot, multi-finger robot has dexterity because it has higher degree of freedom. But the downside is it's harder to control it. It's not easy to control the multi-finger robot. And I think, in today's talk, Professor Shin was also talking about the BLA model. And we are also working on BLA model thing. So in MSR, we are developing this CogAct vision language action model. And it's a kind of, almost becoming like a template. Basically, you have vision model to take the image input, and you have a language model to take the language. Then you output some cognition feature that is an output from vision language model, some latent vector. Then, that is passed to action model. Then action model can be anything, but nowadays, quite often people use diffusion model, diffusion transformer model. And the diffusion model basically takes this cognition feature as a condition. Then it starts from noise, then generates some sequence of action. So that's what's going on here. And these are some of the examples. So basically, CogAct can take the language instruction as input. So you can tell the robot what to do. Then also, it takes image as input, then generate the action that is learned in an action model. Yes, this is a two-finger gripper case. And this CogAct has been trained only for two-finger gripper. The reason is that we have a lot more data with two-finger gripper, but we have very scarce data for multi-finger hand. We basically don't have a sufficient amount of data for training a multi-finger robot hand. That's a current limitation. So one thing I want to discuss with you is about this, generative robot processing. So diffusion model has been used for generating action. So it turned out to be very useful to deal with some multimodality of action. Multimodality here means that, suppose you have the same condition, like the same text input, let's say, grasp this object. But there are multiple ways of grasping that object. How do we reflect that in training? So different people may grasp differently, right? So that's multimodality. So diffusion model can naturally, it takes care of this multimodality, and also it is useful for dealing with high dimensional, reconstruction. So that's good. But if we think of diffusion model, it's really about the generation as sampling. So you wish to, so what flow matching or diffusion model is trying to do is to estimate the manifold of your data distribution, which you don't really know. So if you know this manifold, then you can sample a point on this manifold in order to generate, generate action. So imagine that, this is a space of images. Then if you sample one point in this space, then that corresponds to one image. Then this manifold can be regarded as a kind of set of reasonable images, reasonably looking images, nice looking images. Then if you sample from this manifold, then you are guaranteed to generate a nice looking image. So that's a point of diffusion model or flow matching model. So by the way, so diffusion model, flow matching model, we tend to call them, the same thing, flow matching or diffusion model. We don't really care. For example, stable diffusion 3 is based on flow matching, and it's not a diffusion model. And but there is a clear distinction. So I just want to remind everyone, especially students, if you're working on diffusion model or flow matching, they are different. Their goal is the same. So then the question is how to model, this data distribution, right? Then people tend to start from some noise, Gaussian noise, because Gaussian noise is something it's parametric form. But it doesn't have to be Gaussian noise. It can be any parametric model where you can sample. It can be just a point, which can be regarded as a Dirac delta distribution, or it can be some, whatever parametric model that you define. So typically, we begin from Gaussian distribution. Then what flow matching or diffusion model learns is a vector field that moves that distribution, noise distribution, to the data distribution, essentially. So once diffusion model is trained, it gradually moves your non-parametric form, parametric manifold, to the data manifold or data distribution. So this is what diffusion model or flow matching is doing. Then once trained, because you know that vector field, you can sample from the data distribution by sampling noise. Once you sample noise, then you know the vector field to move, right? So you can move that noise point to the other point on this data manifold. So that's the essence of diffusion model or flow matching model. Then again, do we really need this in action generation? So that's my question. Is diffusion good for action generation? It is quite often used, and maybe yes, for some aspects, multimodality and also high-dimensional, capability. But do we really need this randomness introduced by sampling from noise, or even the Brownian motion in diffusion model, which does not exist in flow matching model, by the way? So this randomness is good for generating diverse output, and people tend to appreciate the diverse output. So when generating images, then you see different output all the time, and we enjoy it. But does robot appreciate it? So that's a different question. If the consumer is human, diverse output is good. But is that the same for robots? As a robot, as a non-subjective entity, I'm not so sure about that. But anyways, the action model part, the trend is we use diffusion model, but I don't think we have settled down about the choice of action model yet. And the other thing I want to discuss is data scarcity in training BLA model. So LLM, BLM are successful because we have data, we have a good model, and we have good compute power. Then we are getting there to achieving digital AGI. But in embodied AGI or physical AI, we are not there yet. Data is scarce. Model is questionable. We don't know which model is proper for this task. Compute power, maybe we have it if we pay. So then, text data, has a lot of tokens compared to actions where we only have 2 mega trajectory as our data set. So once we have a lot of data, then can we really solve this problem? That's still unknown, but we tend to believe that this scaling law we have witnessed in LLM can be applied to the context of BLA. And if that is the case, we may be able to, generate the action just like a text case. So text case is that it's all about the next token prediction. Then you train the network to predict the next token. The action is also a time series sequence. Can we just predict the next action, just like we do in the text processing? All right, so Then, so I'm going to conclude my talk. So I talked about sensing and also acting. And I didn't really show anything new in this talk, but I just throw some questions to you. And for sensing, I believe that more sensing capability is really needed. We need to deviate from just observing the scene by camera. So we may need to invest more on tactile sensing or even more creative way of acquiring the physical property by observation. And also computational imaging is a way to go. We definitely need more, much more accurate, fast imaging technique. And for acting, action model, yes. So I'm not, saying that diffusion model is bad. It's great, but is that really suitable for our task? That's something we wish to think. And the data scarcity is a problem that people quite often discuss. Sim2Real or teleoperation factory, many other ways of is considered, but it's still very scarce. What can we do? So this is an area that we can make impact. And lastly, I talked about learning-based and model-based approaches. And so those two seemingly distinct approaches appear anywhere. So in sensing and also in acting. So if both of them output the same, if both of them can output action, then why don't we just add them and then divide by 2 to make a good estimate? So that's probably one of the simplest way of combining those two approaches. But there may be a much better way of doing it. So what is the right strategy to benefit from both approaches? So that's the question I just want to raise in this talk. Okay, with that, I just want to thank my colleagues back in Osaka University, and also my colleagues at Microsoft Research Tokyo. Yeah, that's all. Thank you very much.
Thank you, Yasu, for a very insightful talk. Do we have any questions from the crowd for our keynote speaker? I'll start that. So on one of your last slides, you're talking about the digital AGI versus the embodied AGI. So the past 10 years, we've seen just tremendous progress in digital AI. So you threw this as a discussion point, but what do you think? Will it be able to achieve this level of success for embodied AGI in the next 10 years?
I think it's highly likely, yes. Yeah, so I guess, there will be a moment like we observed in ChatGPT. Once we have a sufficient amount of, action data for training, then we start to observe, the turning point. Mm-hmm. And then, yeah, I think a 10 years time frame is very reasonable. I think it's likely to happen. That's my guess. Nobody can predict future. So.
And in a way, the action models, it almost seems to me that it's almost the same as a language model or any video understanding model. Yeah. You take images or language, and right now it's predicting tokens or any actionness of a video. Instead, for this VLA, you just are predicting what you should be doing next.
Yeah, I think there are works that uses some state space for representing action sequence. So I don't know which is better. I'm not in a position of commenting it, but I think both of these are two viable hot topics, and I don't know if they are competing, but so we try to see which works better. Yeah.
And so this is something that is not quite related to the actual research part of it.
Yeah.
But the first part of your talk was introducing Microsoft
Yeah.
Research Tokyo.
Right.
So my question is, how can you have our own Microsoft Research Asia Seoul?
Oh.
Can you give us any tips?
Well, that's a very interesting question, and I think Tokyo Lab case, it just happened by chance, and there was some business reason to be in Tokyo, and there was some investment of Microsoft to Japan, and the Tokyo Research Lab was established as a part of that effort. So I guess you probably better talk to more senior people in Microsoft, to see if there is a plan for such investment.
I see.
Yeah.
You have Microsoft Research Asia in Vancouver, right?
Yeah. Yeah.
So we should maybe have one in Seoul pretty soon.
Right. Yeah. Yeah. So I personally agree that regional lab makes a lot of sense because we have a direct access to local talents, and I know Seoul has not necessarily only Seoul, but also Daejeon as well. But I know many excellent Korean researchers, and I personally think that that's going to work well. Yeah.
Okay, so if we don't have any question from the audience, well, let's thank Dr. Matsushita once again for his great keynote speech.
Thank you very much.